I thought I don't have.
Yeah, so we basically say, okay, centralized are very stationary, they're not adaptive, they're based on abundance of the water in that location. And what we want to do is like address the issue of scarcity in the world. Like it's becoming like a huge problem like all over, and it's growing actually. And it's becoming political and like creating conflict everywhere. And then we introduced the idea of how can we like make water available to everyone. And we looked into strategies of people trying to do like cloud seeding, very extreme strategies. And also like people were thinking, oh, can we like bring an iceberg from Antarctica to whatever country like UAE was proposing. And there are like primitive strategies where they're using decentralized systems, like the Warka Tower, where they have these towers in local communities that extract water from the air, basically.
And this is a type of decentralized infrastructure that we are interested in.
Yeah.
So we want to decentralize, we want it to be personalized, we want to control clouds. What if we can do that? And like we're learning from how clouds is formed. It's basically like the water vapor is attached to dusts, and these dusts act as scaffolds, and it condenses on these dust particles. And that way the clouds are forming. So this is our inspiration. We're looking into a system that it should be lightweight. Hence why we're showing the dandelions. We want something that is as this light, that can be moved, floating in the air, and that we can share all over the world and stuff. Yeah, this is basically what we want. We want an agent that captures, like retains water. Did it pause the video? No?
Maybe it froze.
It froze. Oh yeah, okay.
No.
Okay, that captures, delivers, releases, and the water, basically. And we're weather data that we can use.
Inspired by the inspired by the cloud intelligence, this phenomenon. Can you hear me now?
Yeah.
I don't know what's happening with my. Okay, inspired by the intelligence of a cloud, and the phase change from liquid to vapor and back to liquid. We are looking at this process. So how water vapor becomes liquid droplets that stack on dust, and this forms condensation nuclei. So this condensation nuclei and the accumulation of that is what forms finally a cloud. And when this gets heavier, and according to the temperature, of course, it gets formed to crystals or water droplets. So we observe this cloud behavior, and we analyze that in three different behaviors, let's say. So we have the small scale, which is the condensation nuclei, the medium scale, which is the cloud, and it's where the collective behavior is introduced and where we have to consider environmental parameters. And the issue of mobility is crucial. And then the larger scale, which is actually the weather pattern.
Yeah, I would actually call
and we are translating that. Sorry?
I just said, like, I would actually call the large scale the weather. Like you've done it here. The other one was called cloud. But yeah, it's nice. Okay.
Yeah. So we translate the same three scales in our system and the way that we want to examine that. And we firstly saw some studies about the small scale, the agent scale, which is its main aim is to receive humidity, to capture humidity, start floating, and then at the same time it has to protect humidity. So to retain it. So capture, retain are the main goals, and they should also be that light. That we should also keep in mind that they are that light that it helps it float. So looking at these systems was a way that we thought that it could help us create this lightness, our system, this lightness. So we examined these different qualities on Earth, and finally thinking of how these all parameters could be fulfilled. And let's say which is a captured. So there are some green studies here, and then we were thinking about how we could differentiate it, for example, to different levels of two different hair behavior and in this agent, so that, for example, the interior captures and the exterior helps it float.
Sorry, Daphne, I think like you're breaking up quite a lot.
Agent float. I'm trying to fix this here.
Okay.
Okay. Can you see now?
Yeah, that's better.
Okay. So how this can also float and protect, and these vortexes are the ones that help this agent float. So this was kind of the agent typology that we you can speak since I'm breaking, guys.
Yeah, maybe
I will just go through the slide.
Oh, yeah.
Like breaking.
No, you do that, you said. Okay, I'll share my screen.
Yeah, it'll be better.
Can you see?
Yeah, that's fine.
So yeah, we're looking at like different strategies, like how these agents would have sensors and like they would sense the humidity in a place and react into how they would open and like capture the water. Basically, this is like a snapshot of what could possibly be our agent. How we are looking at these strands with capture and then directs the water towards the center and retains the water there. These are some of the experiments that we've done. We've done with the liquids and we also done experiments. They're very basic experiments that we've done. We were looking at what else can hydrogels do in terms of like not just like in terms of duration, how much water they would take in within the duration time and how much they would release. And then we've added a couple of simulations that we've done before. This is viscosity. This we've done it before, like before mid-review, and we tried to relate this to our concept right now with the fluids. And then back to our like the initial studies of the particles in unity, and how like we've like we were able to get patterns out of these particles in unity in terms of like the forces, the separation, these rule sets, the attraction and the alignment. And like we were looking to phase change and what it is in our project. So this was unity work like a while ago, and we've stumbled like in several problems, but we managed. But the thing is with this one, the patterns, like they were repeated. I'm not sure if it's like, we're not sure if it's like successful or not, but there was not much out of it except for what we have now. And we added temperature, and we had some problems with temperature in terms of coding. Like we wanted to localize temperature in different parts here, but unfortunately it kept adding temperature throughout the whole population, not localized like what we wanted to do, so that we can see the phase change within this one population. So we were trying to make sense of what this would be. So we layered out the patterns that we've got, and okay, we said, okay, these could be the layers of filtration of water, directing the water, and storing water within our like system as a material.
Yeah, but this was the older part of the work where we were considering the materiality of a material that can direct, filtrate, and storage, that we don't really know. I mean, if we could apply that in our work right now, because it's not directly in a direct way applied.
No, I understand.
Yeah. And these are material studies of the textile, how we can like direct water using this material. And then back to what we've recently like presented are these agents and how they would behave in terms of the capturing the water, and in terms of this is a simulation that should show some behavior. And then
it's just a short behavior, using the agent accumulation scale.
Yeah, now like the medium scale, which is the accumulation scale, how they would behave together, not just one agent. And in this part, it's the release part, where they would release in two ways, like either as rain or as snow crystals. And these are Maya simulations. We were looking at how
for this Maya simulation, we try to use the point cloud to add different turbulence and different values to generate different paths and patterns to see the results as as a catalog. And maybe next. Next page. still with my with larger population of M particles and trying to add. We are thinking to use large population to absorbing the water from moisture. So with this wind turbine and the tunnels to capture the moisture from the air. So we did some simulation on this part. And next. And with the simulation, if we can change that particle system to release the water and change it into mesh system, so it's maybe some way we can look into with. Okay, next. And with the particle fluid, we add some constraints at certain point. We try to control the pattern of the fluid of particles with different values. So we did lots of catalogs. Okay.
Mm-hmm.
We were looking at how we can control how to release water, basically.
I see.
And then like we were looking into what about one emitting point of water release, and then how about multiple water release?
Mm-hmm.
And also because part of the release would be like crystallization, like in a form of crystallization. We were looking at how we also accumulate these agents together. How would they connect? Maybe they would connect through crystallization through this phase change. So we were looking into, okay, we can add several nodes of crystallization, and maybe they'll branch out and then connect through phase change. And then in this scale, it's the weather scale, where we address the humidity demand. Okay, here it is. So basically, the agents would search for humidity. Do you want Yuji to speak about this?
Mm-hmm.
These are all Unity work.
Mm-hmm. Okay.
These are a few simulations of the agent's behavior.
Mm-hmm.
Like obviously we still need to work on the simulations, especially these, like the one that shows the swarming.
Mm-hmm.
And then this is like it shows
Mm-hmm.
like when it releases the water, how would like people behave, and like how yeah, we can show the other one. So this is mid review, post mid review.
Mm-hmm.
Found this one.
I can only see the PowerPoint with the dandelion looking
Really?
thing. Yeah. Is there something else you're showing?
Yeah. I think I should. Wait.
Can you hear me now normally? Sorry, I'm
Yeah,
not
we can hear you.
okay.
Okay.
Now is it better? Okay. So this is post-image review.
Mm-hmm.
We're not gonna go through this. We just went through this.
Mm-hmm.
So basically, capture, retain, deliver, and release.
Mm-hmm.
And then we were like dividing the whole for goals and in what scale are they should be. And for the agent scale, okay, we were like, okay, it should be where the capture happens and the directing of these water and the idea of floating this agent. As for the deliver and release, deliver it would be in a cloud scale, an aggregate accumulation of these agents. How they would go to this, how do they respond to the human data? How would they go there? How would they like together and how they would capture and also like deliver to the people like in a cloud way. And then the release would be in the agent scale. So each is each category, like we described like what are its properties, basically.
What are the trigger points that we should consider? Yeah, in each category again. And the goal would be to describe finally a circle of events based on these goals. So we are now struggling to develop the agent given these main goals that it should have. We don't have much yet to show on that, but these are the main questions that it should answer.
So are these questions relating to what you see as the prototype, or just an agent in any sense?
Yeah, I think they should be related to the prototype, to the agent, to the typology of a single agent.
Okay.
It should be able to address all these questions. So from capture to directing water to a specific point that it can hold it and retain it, and then also remain lightweight in order to float, and then which is the factor that triggers release of water.
Yeah.
And then next.
So one of the simulations that we're trying to do, is it showing it? No.
No.
No. No.
No, what?
No.
Maybe. Yeah. Oh, yeah. It's true.
Yeah. Well, I can see it.
Okay. So we were like experimenting with the agent itself. How about there would be like a system that would like as it captures water, it would grow and then it starts to close and protects the water, basically.
I see.
Houdini work, and then.
And I try to build the model from Maya, but in this way I think it's still not working out because it's manually built in this case. But I want to ask you about like if in Maya also can simulate to generate this kind of form by like grow system or other like mesh animation. Because in this one, I'm also trying to use a mesh to simulate the mesh system to capture water. The purpose is this, but I think to get this result for now, if it's manually, so it's not right yet.
Okay.
So yes, these were some in different directions that I think we said that we will focus more on the agent that we showed before.
Yeah.
We also have some tests in porosity and some, but let's not focus on that because we said that we don't develop that further.
Mm-hmm.
And the bumpiness of the surface.
Yeah, basically why we went through this, because we wanted our agent to exhibit properties that help in, you know, capturing water, and bumpiness is one of the properties that we need.
Okay.
Yeah.
Mm-hmm. Is that the end of the presentation?
No. Okay, this I showed. So going back, like we showed you like a couple minutes ago about the weather data and the Unity work.
Yeah.
And when Theo said move it to 3, was the latest work, moving that simulation to 3D.
Mm-hmm.
Sorry for the internet. Okay, here it is. So now,
Okay. Mm-hmm. Oh, I see. Yeah.
Yeah, we were thinking whether the cyan agents should be the humidity agents, that is gradient and not so uniform, or we should focus on them being our agents that respond to humidity goals or to demand goals.
Mm-hmm.
Because maybe we should, before we had defined humidity as a simple goal, but humidity is never, and we were thinking of defining that with different influence areas according to how large is the area or small, and the same for demand according to how large is the demand or not. But
I see.
Yes, but we were thinking that maybe humidity, for example, shouldn't be just a point in this simulation. Should be a gradient.
No, like humidity is for sure a gradient, like because it occupies the space in a way that's not like necessarily localized. Like it's more of a distributed condition within your voxel field, where each voxel can have information about what the humidity within the voxel is. I think that's the most obvious choice, because your humidity could be an underlying environmental information underneath your particle-based simulation. So once the particle passes through a certain voxel, the voxel contains information about the humidity, which the particle can react to or modify if that's what we choose to do with your system. So maybe the particle also carries its own humidity with it, meaning the amount of water that wants to release or wants to collect, and then whatever's in the environment can be redistributed by the agency of your units or your population.
Yeah, and we tried also to see what this gradient of humidity is by importing some humidity data from NASA.
All right.
to create this graded atmospheric field. So we are at the point that we're trying to, we found a way to read that in Houdini with Python. So this is not using a map. This is only using coordinates and humidity values and setting a color mapping for humidity. But we can clearly start seeing which part of the world is this. I mean, if you go to the previous one, the map one, who's sharing the map? It's this part with Egypt, Sudan, and
makes sense.
Yeah, just to have the image, the full image. Libya, Egypt, Chad, Sudan, and UAS. So we started seeing then, this is a voxel-based environment, and we started seeing how we can translate these attributes, these humidity attributes, to other kind of attributes like scale, for example, here, or next one, scale again, or next one, the position, or the Z, the scale only. So these are some, they don't say something yet, but we're just trying to show or to explore how we can extract this information and transform it to something else, or to use it in another way, use these attributes. And actually, we are stuck on the point that we're trying also to implement to import other databases too, like temperature, atmospheric temperature, etc. But it has to do with the different file types that NASA uses. And there is a system which is called AIRS by NASA, and is recording the atmospheric data, which is very different. And maybe because the amount of data is bigger, it's a different file type. So we found a formula that we could translate that through Python to a CSV file. With a CSV file, then we have found a way to read that in Houdini. But we can't translate that yet to CSV, and this is like at the point that we are kind of stuck right now regarding this. If you have any experience with Python, it could be also helpful. Maybe you could. There is an asset in Unity for Houdini, but we haven't really explored that yet.
Okay, just give me a second, and I'll come back in like a minute, and we can continue our conversation.
Daphne, do you want to show that file, the IBTN thing shit of yesterday?
If Alex, sorry.
Yeah.
If Alex wants something relevant, could be useful. I have this,
Yeah.
I think that this last part of Unity work and
the Unity work
is important to think how we can connect that.
Really? Did you- Yeah. Yeah, if you call the children, yeah, that makes sense. Oh, well,
But I don't think that we need the local temperature right now in any way. Not that much.
we can we definitely will be addressing the temperature and local temperature and these things. So
Yeah. The situation with my IP is getting worse. This time I had to run some commands in the terminal.
again,
Yeah, but
the Wi-Fi.
the way that I have had found to fix, I had done that before, so it didn't work again. And this time I had to run some commands from terminal to connect to the IP.
You're going backwards. Maybe if the school has an IT, I think you like they do have an IT. Tell them like fix it permanently because it's annoying.
Oh my God.
You have to every time
Reset the IP.
No, definitely email the IT and tell them, okay, I need help.
Yeah, I think I shall. The lab is not open.
Who told you, Yuji?
They told me it's not.
Really? Okay. The AA is open, the rooms.
The AA is open. The lab, they said that it's not open. That's what they told me. I don't know.
Okay, I'm back. So concerning all of this information about the weather data that you're collecting and how to import it into other platforms, I'm actually more interested in understanding what it is that you plan to do with this data once you've managed to import it into Unity or Maya or Houdini or wherever. Because I think for me, what seems to be like the most pressing answer that we need to find, or like a question that we need to address, is that once you have all this data about humidity, for example, will let's say the simulation that's run on top be about like, oh, let's redistribute it while somehow maintaining the amount of available water, or like what is it that you hope to achieve from it? Because if that's something that you want to do, I don't even think that we need to be stressing too much about importing actual weather data yet. I think an abstract representation of that redistribution process would be enough.
Yeah, we like the idea of responding to actual weather data, because we have also the large scale, which is the weather system, and we like the idea also discussing that with Theo, that we are trying to localize that somehow. But it's true that it's not that important to have the real actual data. I think that the intention is to also, if we are able to set a rule through that, we kind of respond on how much humidity we want to collect and how much humidity is enough to collect, and how much the agent can travel, like for how many meters or kilometers to transfer the humidity, and how much humidity it can collect through this traveling. So
Yes.
this is pretty complex as an assumption. We can't do that without having at least a gradient map of values on something.
Yeah, but I think that gradient map in the beginning for our own understanding should be just anything. Like it should just be like dots, like two circles on a field that say this is super humid, this is super dry. Like I just need to think that the way that we set up this this test needs to be first very, very simple so that we can have proof of concept, right? Like I'm not even sure like what's going to happen fully with it. You know what I mean? So it's kind of important to see whether we can get anywhere in the first place before introducing, let's say, large-scale weather data from an entire continent, for example. Because like I think before we go into something that's super specific, like actual data, which I think like you were already kind of discovering ways in which to convert something to like a CSV file, that is already pretty much importable anywhere. But before we get to that technical issue, I think the first one is maintaining like how this computational model will evolve, because I also think that the earlier stuff that you did was concerned more with like phase changing. I think it can be hacked to talk about this new new like setup that you want to create, but I think it's more about creating it first and seeing what it can even yield or how we set it up than operating on data that's like concrete or coming from the real world.
Yeah, the thing is that if we want to speak about clouds, a cloud is so complex as a phenomenon that it's not that we want to explore this behavior that is based on this complexity of data, I think. So we can have the simple scale of the like setting very simple rules, but I think it's important to speak about the cloud to have a larger like.
I understand. It's just that the logic follows that if you're able to import a very simple map and run a simulation on top of it, you can also import a very complex map and run a simulation on top of that. My point is that it's like we first need to do something simple to see what the yield is at all. Like it might be that you will find that, you know, it's very difficult to set up the rules in this way, or something will go wrong, or you'll find out something else. But I think like before, like complexity is never the place where you start. Complexity is reached slowly with you know, a battery of tests that you run on top of a certain setup. So I understand like I get it. Like when you say like we're exploring the weather or exploring clouds, like we can't start with something that's like 2 squares on a field. But in fact, like that's the safest way to start, because that's the safest way to set up your computational model always. So I think like if we're talking about this sort of exchange of humidity between environment and agent, there needs to be like a serious conversation about how is it that we envision that we're doing this and what are the constraints, because you already are going to the territory about talking about the prototype. You kind of have this idea of how the model you think might look like, which is good. But we need to abstract its properties into something that's like computationally friendly. Like if you're saying, you know, this first test that you were showing with NHAIR, we're saying that has a certain capacity of humidity that it can carry, then like, okay, that sounds good. But how does that change as that element moves? Like, does it dissipate? Does it, is there a tension complete? We can also talk about, I think you kind of touched upon in your physical test that you're trying to set up. I think it's quite interesting, this idea that like you're saying, I'm not saying this is exactly what your prototype is, I wouldn't say it, but like let's just kind of say it in a very general way. If you have a certain amount of dry hydrogels, you send them up to the atmosphere, and then in like a cloud formation where there's a lot of humidity and it's almost about to rain or whatever, like these hydrogels start amassing a lot of humidity, and then like they incorporate it into their volume and their weight, which makes the element kind of fall down to earth again. So you're kind of talking about this redistribution system, which is also dependent on the amount of substrate that you carry with you. In this case, it's water. which might make your element, more or less weighty. Like the mass will change because of how it's collecting water, which I think is an interesting concept to explore as well. So it's like you can say that these like very, very light feathery dandelions, they go up because they're light, but then at some point, because they amass so much water, they go back down. And like, can we set that up as a system as well? Or how would that look like? You know what I mean?
Yeah.
So I think like the first step would be to start thinking about how we distribute this humidity and what are the actual constraints of how humidity is distributed. Because we can, obviously we can just say there's like a voxel field with humidity information and there's particles that move through it like without, like they're just like moving around like a swarm. But what does that mean? Like how can we set up, like you were saying also, what are the trigger moments in which humidity is released? Like what is the outcome of this simulation? It could be something like we have a cloud of agents moving through the field, they collect humidity, and at a certain point there's like a trigger event, like you're saying, in which it releases all the humidity it contains back into the environment. And then we see what that does to the environment. Because also, once you redistribute humidity within your environment, you can also talk about like, okay, if I dump enough humidity in one area, it might form a cloud, you know what I mean? Or like it might change the weather conditions sufficiently. And I'm saying that like this might happen on like a super large scale where you have like, I don't know, tens and hundreds of thousands of your units like working tirelessly to kind of reform the weather pattern in a certain area. And looking for ways in which that can also be an energy efficient process, because it sounds like it would be very costly. So like you're basically creating a separate system to the weather system of that already exists in nature, which has this idea of like redistributing humidity in a way in which it can affect scarcity of humidity in certain areas. And now how do we do that in a way that's also like intelligent, beyond like saying, this just kind of carries water with it and dumps it in another place? Is there any way that we can create like a relationship between, its weight, the way that it falls or lifts based on how much humidity it's carrying? Because if you think about it, it's also how air works, right? Like depending on the temperature of air, it rises or falls, and it is basically what creates the weather conditions as we know it, like the clouds and precipitation. So we're looking at all of these elements in order to set up whatever is happening. Like, for example, this simulation for me, like that we're seeing right now on the screen, I think it just requires tweaking. Like we need voxelized environmental information in the background, and we have particles that have certain properties that change as they move through this field. And the triggers are set up based on what it is that we want to achieve. Maybe we were saying that we're allowing particles to travel a large distance before releasing the humidity or something like that. Like it needs to be some kind of an abstract goal just in the beginning so that we can try setting up this model first and then seeing what the outcomes would be. Does that make sense?
Do you think that the environment, our graded atmospheric field, let's say, should be voxelized, or also in the Unity work that we should depict that as voxel space? Or
I would say so, because don't forget, voxels can be very fine, right? Like you can end up having a very dense voxel grid if what you're looking for is high resolution. Or it can be like a point in space that sort of creates the values that are assigned to your voxel field. So if you have like 6 points that are saying like, depending on your distance to me, I'm applying a certain amount of humidity to you in the initializing frame of the simulation, then you can just control what kind of resolution you want of that space by controlling the amount of voxels that actually make up the space. It's like a weather balloon, right? Like the reason we get weather data is because there's like millions, I'm assuming, weather balloons all across our atmosphere, and they're like point information in one place, which then interpolates the information between itself and the closest other weather balloon. We can't feasibly sample point each atom in our atmosphere, but we can derive information from weather balloons that are in relatively small distances and then infer information in between.
We actually have also optimized the code with spatial binding. So this spatial, we were thinking at some point whether this spatial binding could be a way to see that as a voxel-based scale, as a voxel space.
Yeah. Look, on like a very, very, very low level that you never see in software, everything digital is voxelized. Like that's how computers work. But I'm just saying it like your environment should be voxelized because it's really easy to follow data points in a voxelized space. They're like points in space with data attached to them. And the data can change based on what passes through the bounding space of the voxel, which in your case is this agent that's flying around. So now we're talking about like, if we have our agent, which carries a certain amount of humidity, it has a certain velocity because it moves, and it has a certain trigger event that makes it either release or suck up humidity from its environment. What does the environment look like after frame 5, 10, 20, or 300? Does that make sense?
And I'm sorry.
Okay. I think so, because the simulation in its like in its, let's say, result, if such a thing exists, is this idea of redistribution of humidity, right? So we're just kind of making the point that the agents that you have in your system are how this humidity gets redistributed, but the event space or like the environment itself is what we care about, because we're saying we want to take the humidity somewhere else. So if that's the goal, or if that's like the attempt or the wish, that's what we're following, right? We're following changes in the environment, not necessarily changes in the in agents. The changes in the agents just facilitate how the environment will change. Because all things being equal, you're basically saying if our agents are not there, then the situation should just follow the weather pattern, and that's it. Like it's not going to change.
So we could state that our humidity agents, not our agents, the humidity which exists in the atmosphere is following a swarm system, but divided in a voxel space, which voxel space has different qualities.
Yes.
And then our system is a slime system, and it collects this. It moves through this swarm humidity space. I don't know.
Basically, voxels are always fixed, right? The only thing that changes for them is the value which they store, but they occupy the same space. Your agents are not fixed. They go wherever they want, and with them carry information about a certain amount of humidity that they have. They can choose to dump it out in a certain voxel or suck it up from it, but after every frame, the voxel space that describes the humidity of your environment should change. So like in the beginning, maybe everything was like everything in one corner was like super dry and everything was super humid in the other one. But then after a few frames, like your agents have already started redistributing this. So they will take up some of the humidity from like a super humid area and then travel through a couple of voxels and then decide, okay, I've traveled through enough voxels, I need to dump out my humidity here. Do you understand what I mean?
So would that show like the some form of negotiation between the agents? Like, do we need to show in a code of line that they need to negotiate each agent? Okay, if this voxel area has a humid of blah blah or like 50%, don't go there. Go.
Yeah, you can do that, or you can also say like, if there's 16 agents all of a sudden occupying one voxel, they are allowed to release all their humidity, and that creates a certain amount of water in that area. So like that affects scarcity or something like that. Like basically we're looking for ways to invent triggers which will lead to events that actually change your distribution of humidity within your atmosphere. Does that make sense?
Yeah.
And I think like the trace of that is like your space making strategy. Because then like once we have that up and running, you could basically say like, okay, maybe it's just about there's more water here now, so we can do something there, or like people feel a greater level of comfort because there's water where there wasn't before. Or you can even say like maybe it's just like substrate or building material. It can really be anything. It's just about saying that it's in the end a management system, and there are certain events which lead to the distribution of a certain resource, which in your case is water.
Yeah.
And that, you know, becomes embedded in this voxel field, which becomes like a notational system or whatever is happening within your environment. And we can relate that to space making. We can relate that to infrastructural changes. We can relate that to the fact that, you know, to farming. We can say like you can farm here whereas before you couldn't, or something like that. Or harvesting as well, like because you can take water from certain areas rather than release it there. It's just like it's just a resource management system in its most basic form. Yes. Oh, you define however, like in the first frame, just apply it however you like. Like you can just put in an attractor that assigns values. You can paint the voxel and tell it like this is your value right now. It can be completely arbitrary. I would say make it just simple so that we can see what happens after a couple of frames. Because if you start with something complex, you're just going to end up with like a jumble of things. You will never understand what really happened. But I would say like just say something like, okay, so all the voxels that are below Z of like 10, they all need to be humid. All of the ones that are on top, they need to be dry. And then you let your agents do the redistribution. Does that make sense? And then eventually, like you were saying, that can become an actual weather map, and we can say our voxel space is now massive and it's covering, you know, the whole country of Egypt. So this is what we have there, and this is how we could redistribute it, or something like that. That's fine. Like that can happen later.
Yeah. We were thinking that we should move up just forward 3 scales on parallel, because we don't have time to focus only one thing. We're 4 people. So, yeah, we agree on that. It shouldn't be the solution from the complex scale. Yeah.
And I think like your research that's talking about the unit as well, I definitely run that by APO as well, because like you're getting into like a design of the object, right? Like what I'm talking about is just a system which supposes the object can do this, but how it does it, that's a separate issue. Like this kind of stuff that you're showing on slide 10, for example, that's like a conversation that you also need to have with APO, saying like, okay, our unit needs to retain and release water. How can we do this? And then in the simulation, we're already assuming, okay, the unit can retain and release water, but what does it do once it does that? Like, what's the outcome of it being able to do these things?
Yeah.
Like I think like as a unit design, this is starting to look kind of cool. Like I think it could go somewhere. I do think that it kind of uses some of the knowledge that you probably collected from like the use of mist catchers, which are I think extensively used in South America, especially in mountainous regions, because they can collect quite a lot of water. You're just turning it into also a mobile system. It's not just fixed in one place, but it can go elsewhere. So it's just about like that design part of how the unit will look like is like a separate strand of research that only what it gives to the simulation is only the knowledge that you can do something. Like you can say, I can collect and release water, but how I do it is a separate research. So like as you were saying, 4 people, someone can work on that.
And the floating part, like the floating part is what we're trying to address. Like how can we make float And when it gets the water, like what happens, and like they should like the weight of it.
Yeah.
And
I mean, I think like the weight of it can also be something that you explore in a simulation, because it's basically just saying if you have a lot of humidity, you're heavy. Like it's just a buoyancy simulation, right? So you can test for that as well. But as to how the actual locomotion works, like how is it able to like float or fly or steer, that again falls into the category of designing the unit itself, which is a conversation that you need to push forward with Apostoli. But I think like obviously whatever you can do to make it as passive as possible is always a good idea. Like you don't want like a particularly heavy thing, which is why I'm saying like it's also a nice touch if you would incorporate this perhaps even into your simulation, or like saying, you know, it's almost like a hot air balloon, right? Like it has ballast, so it's weighted down, but then it rises because of the heat. It's just in your case it will be something else, like the reason for rising and falling will be the humidity and the amount of water that it's collected. Like, you know, it kind of goes up, collects water, gets really heavy, floats down to earth, for example, releases water, and for that reason it's again released to fly or something like that.
Yeah, this is a question that how we can simulate that for us too, because the way that we saw the agent until now, we worked on that. It was more intuitive, like the intuitive understanding that larger surface, which we get with many hair, like
Yeah,
and
that's just a vector, right? Like it's basically like reversing gravity and then also applying a weighting vector to each of your agents, basically saying if your humidity score is 5, you are weighted down by a vector of 5 that is pointing down. Otherwise, you'll just float, because we're assuming that your elements are lighter than air, like they're helium, essentially. So we're saying, like, if you're in a position where you're amassing too much weight, you have to go down. Otherwise, because helium is lighter than air, you have a constant up vector that's pushing everything up. Does that make sense? Like it's just about applying
this
a
be
force.
helium?
Sorry?
You think should this be necessarily helium?
I don't think it should be. I'm just kind of putting it forward as like a proposition, but I don't think necessarily you need to integrate helium into it. Like obviously it can have some kind of propulsion system. We can just be making the like the case that because it needs so little to propel up, because it's so super ultra light, that we're also conserving a little bit of energy. Because I'm kind of concerned about like what the kind of questions that you might attract if said like, oh, it's a quadcopter that literally goes up and then goes down. You know, it's like a massive consumption of energy, and for what? So I'm saying like if it's like an ultralight material, ultralight unit that has very little propulsion or steering needs, and then it also depends on this, like I'm going up because I'm dry, I'm going down because I'm damp and full of water. Like it also kind of tries to address the system in a more passive way. You know what I mean? Like I'm just trying to make it go in a direction where you won't have to think about like a question that might be raised that's like, wow, that's a really inefficient system. Like you're trying to emulate something while also expending insane amounts of energy for no reason. And I think you can explore like other phenomena in nature that like capillary movement, like in general, like water retention. There's plenty of like physical materials that, you know, chemically react to water in a certain way, like hydrogels, like other elements, like you know, hydrophilic natural materials that change their shape based on humidity. I think like everyone and them and their grandmother at this point has seen the Akimeges, like hydrophilic pavilion, the one that kind of is from those bristlecone pines that curve when there's humidity and then are super close when it's dry. And like all of these like passive systems can also be integrated into the design of your unit.
So how detailed should we be in the design of the unit? Like we were thinking of like each strand of this light system. Like, are we supposed to show what it is? Like, is it a smooth, or it has like some type of like bumpiness
I mean,
into it? Like we were, yeah.
I would say that like the design of the unit is always dependent on what the team can deliver, and it's also constrained in the case of your generation with like other unfortunate, circumstances that we're dealing with right now, namely the coronavirus. Obviously, you should go for whatever you think would be the best product. So like there's no fixed brief that's saying like it needs to be this, this, and this, but especially now. But I think like if you're talking about something like this is such a lovely detail, right? Like you can kind of talk about it in a way of like, oh yes, we can, design the microtexture of the strands in our prototype, and then talk about like how that really improves condensation and the retention of water by an amount of percent of change in the system, and it's like much better than if it's smooth. Like obviously that's a strand of research, is completely valid and very interesting. It's just about like whether you can execute it or not.
Do we have to put like, should we do like some physical experiment, like these kind of details?
I personally don't want to like say, like I wouldn't use have to. I think it would be great if you can. I know that the facilities are limited. It's facing challenges that previous years didn't. This is also a conversation between you and Theo, I think. Like that you should like point blank ask him. Like I wouldn't put those pressures on you, but I'm not sure how the course wants to treat the deliverables in this year fully. Also something that you can discuss with Apo, because he's in general super helpful when it comes to prototyping. But I wouldn't use the word have to. Like I think it would just be great if we can see more research, obviously, as always.
But should we, I mean,
I think like these models definitely perform better as physical models if they're possible. In Maya, I am struggling to think of how we could abstract this process into showing, bumpy surface versus smooth surface water collection. It seems like quite like a complex simulation for a digital space, whereas it's not in the physical.
there is 17 and a 10.
Sorry?
Yeah, it's not like we did this on Maya, like a very basic simulation. So do we just?
But I think personally that the physical experiments should be more focused on the main idea, which is shown on slide 19, of how this floats and how this remains lightweight, rather than on details. But I don't know, I'm just discussing.
Yeah. No, I mean, it's fine. Of course, like locomotion and stuff like that, water retention, those are like the meat of your project. So they need to become like something that's a priority in the model. But it's totally fine to also, discuss this, even if it's like not executed perfectly, but just to show it as like an additional layer of thinking that you're attributing to your prototype, which I think is fine. Like and obviously it's like a very like a logical thing, right? Because it's bumpy, it will condense in a different way, it will direct water, it will also, it's kind of like also putting like a, I don't know, something that's like very coarse, like sand into a fizzy drink. Obviously, it promotes this process of foaming. So this is quite similar in the sense that like a smooth surface will struggle more to create a droplet because there's no geometry that promotes movement or promotes like change in distribution. So it can also be like, it's also completely fine for it to be like a more speculative part of your research project. I'm not saying that you're like bound by law to like execute this in physical as well. It's just simply a nice idea, I would say. Nice touch. Okay. Any other thoughts you guys have?
Kula, you wanted to show the simulation or not?
Which one?
the-
I'm not sharing the screen.
I'm sorry, I'm confused. Okay. Yeah, I wanted to ask you, like, if you have any experience with Python, if you could help us on something.
Concerning what? I might know. It's just that you need to be a bit more specific.
Yeah.
You want to share your screen? It's just like we're trying to open a file, which is in. She's going to show you the.
This is the level the type of data that NASA uses for the atmospheric data. And I actually want to open this file.
Yes.
This type of file that I found as a way to convert the HDF5 file that NASA has to CSV.
Okay.
But I tried that to open with a Notepad, Notepad++.
Yes.
Using this code that actually translates the information that exists in the HDF file to cells, and it gives the cell types, the longitude cell or the latitude cell and the value cell.
Yes.
But the CSV file is never written. So here it was supposed to write the new CSV file, which comes from the HDF file that we are using here. But it doesn't read it.
So it doesn't read or it doesn't write? Which one is it?
It doesn't write, I think. I can't run it even. I mean, I don't know. I thought that I could run that.
Are you sure that all of your paths are correct? Like the paths for reading and writing in terms of like where it's supposed to be?
Yes. I just copied the path.
Yeah, okay. That's good.
And maybe I shouldn't open that with Notepad. Notebook, I don't know.
Did you ever try to feed that file into Grasshopper? Like the one that you get?
The HDF or the IPNB?
Either. Like CSV for sure can be read, but I think like Grasshopper very easily translates files to a CSV. So I'm not sure whether it would recognize the file that you already have.
We had created a code for translating to CSV. I mean, where is that?
Because I'm assuming that whatever you're getting from NASA, like the reason why it might be struggling, it might also be that the amount of information is massive.
No, I deleted it's massive because it's for the whole globe, but you can select the coordinates that you want. So yes, we didn't use the 3 trillion data that NASA has.
Because like I'm assuming that also like kills it immediately.
Yeah, what did we do here? I don't remember. We were here we were placing the file from Unity.
Yeah.
We exported that to coordinates, but I haven't tried the CSV file.
CSV for sure. You can just drop it and it will be read. But the other ones, I'm interested in whether they would actually be read. Because sometimes Grasshopper is able to interpret data.
Okay, so we can try whether Grasshopper can open the HDF, because we want to open the HDF and translate that to CSV.
Yeah, yeah.
Yes.
Google this file type. I've never seen it. So is the HDF file that you have, is it already the one that you've limited to a certain, certain tile, so it's not like trillions?
No, just when I have the CSV, we can open that on Excel, and I delete the cells that we don't want.
Yeah. Yeah, I think
Because
like even in Grasshopper, it also there's like HDF recorder file that's written in Python, but it might exist as like a component, so that you don't have to write it.
okay.
Let's see.
And Alex, in this case, if the Bifrost in Maya can also help with the simulation or no?
I don't have much like experience with Bifrost, but I think like what I've seen from it is that it's mostly about creating like believable versions of like a physical representation of water or ocean, and I think recently even cloth. I think it works like similarly to Houdini actually, because it also uses nodes.
Yeah.
But I'm not really sure how we would implement it for this.
Okay.
I've only worked with Bifrost for like simulating water surface behavior for like collision of objects inside an ocean or something like that, and for foam. So I
Okay.
didn't really use it for anything else.
Okay.
Okay.
Okay, what is this? There seems to be certain libraries in Grasshopper that are built for HDF files. So you might want to research that first before you try to code it on your own. It might be that it's still possible to do even without.
Interesting. The HDF.
Yeah. Like the file that you're mentioning, I think that there's some libraries in Grasshopper that are dealing with those kinds of files. Because like weather data is also, I think, kind of like GIS, so there might be something that they already have.
Is there a plugin? I didn't find any plugin.
So, nope. I'll try to look for it as well, because I feel like this kind of just file interpretation, that should be automated. I'm sure there's something already that you don't need to work for.
No, thanks a lot. Thank you.
Okay, so I think if there is no more thoughts, let's just move on to Air Team as well and see what's happening there.
Thank you.
No problem.